Swayam Prabha. Digital India. Educated India.
Okay, so good morning again. So today I'm going to tell you how we can use uncertainty to say some certain things about our world. So let's first start with a small game. So let's say you have 3 friends, okay? And I just take out one rupee coin from my wallet and I start flipping it, okay? There's one friend who says that if you flip the coin 100 times, the number of heads that I will get will be approximately 50%. So let's say that he says 50%, it will be between 45 and 55. Okay. And he says that if it is falling within this, then you have to give me 10 rupees, otherwise I will give you 10 rupees. Let's say something like that. Okay. Then you have another friend. She says that I have 1,000 coins, or I flip the coin 1,000 times. Same condition. 45, 50, 55. If it is between 45 and 55, then the friend wins. If it's outside, then you win. Okay. And then there's third friend who says, okay, 10,000 coins. Okay, 10,000 coins, same rule, between 45 and 55. If it is falling between this, then your friend wins, otherwise you win. Okay. Which game do you think you are most likely to win? First one. Okay. And why? Yeah. It will become closer to the ideal probability. Okay. So, and how do you, let's calculate that and then we'll run a simulation to see what happens. Okay. So, okay, I have one coin, and so it's, let's say, heads and tails are equally probable. And what would you get what is the probability distribution for, let's say, heads is 1 and tails is 0, right? So it's half and half. That's the probability distribution. Okay. If I am tossing the coin twice and I'm taking this number as number of heads divided by, so this is probability of, so let me say Z is equal to number of heads divided by number of tosses. Okay. So this will obviously be between 0 and 1, right? The number of heads maximum can be this. So what will the probability look like if you are doing it 2 times? What will be the probability of getting 0? 1 by 4, right? Why? Because you need both of them to be tails, right? What about having both of them to be heads? Again 1 by 4. What is left? You can have 1 head, right? 1 head, 1 tail. How many ways are there for that? 2 ways, right? Okay. So you already start to see that it is doing something like this, right? What about, let's just do 3 and then we'll go to the simulation. Okay. Again, I put 0 and 1. What about what is the probability for having 0? 1 by 8. For 1, again 1 by 8. Why? Because you need all 3 of them to be either to be the same, right? So it's 1 by 2 and 3 times. In between, you have the possibility of 1 and the possibility of 2. So what will this be? Okay, let's calculate. So here you need to have 1 head, 2 tails. How many ways are there for this? 3 ways, right? Because you can have head, tail, 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 head, tail, or tail, tail, head, right? What is the other? So this will give you 3 ways. So this is 3 into 1 by 8. Why 1 by 8? Because each one has probability 1 by 8, right? So you will get this. What about this one? Same, right? You can see it because the sum should be 1 Or you can see it in this way, that you can just replace head with tail, and then you're asking the question how many ways you can have one tail, right? So you will get this, right? Okay. And so you again see that this is becoming like this, right? So now let's see if this works. Okay, so let's say probability of bias of coins is this. Coins per trial. Okay, so this is when this is not the probability distribution, but so this is the exact probability distribution, right? Now, if I actually toss the coin, let's say 2 times, right? And I look at the histogram, right? Then 1 point might be 2 trials. So first time I toss the coin 2 times, let's say I get both heads, right? So then I get both heads, and then the next time I toss the coin, I get head tail, right? So if I draw this, then I will get a histogram that looks like this, and then nothing, right? But this doesn't exactly look like this, right? Why is that? So when will I get this? When you take basically an infinite number of repetitions, right? So now I've just taken 2 trials, right? Let me say that I make the number of trials 10,000 or 100,000. Then you will start to get this closer and closer, right? Because what is this telling you? This is telling you what is the probability that you get this, right, out of so many trials, right? So given infinite trials, the number of trials that will give you this will be this much, right? So the 50%, 25, 25, right? So here the number of trials is small. I made the number of trials equal to n square, where the number of, which is the coins per trial. So this number 10 is just telling me, so over here I have 2, right? 1 and 2, right? Number 10 is that I am flipping the coin 10 times. Or you can think of it that I have 10 coins and I'm flipping them, right? And then that is 1 trial. And then I have that many trials, okay? So now let's see what happens if I increase the number of coins. So for now it's 4,000 something, right? Okay, this is too much. It's not very clear. I make it a bit less. Okay. Okay, so now the red curve is basically what the exact one is, that the one that you calculated, right? And the blue is what the data we are getting, right? So we are flipping the coin n square number of times, so this is n. So n square will be whatever, 200, approximately 300 square, whatever, 90,000 or something, right? And then you will get this. So now you can see that within, so okay, so this is 50, 25, maybe 45 is over here, right? 45 is here, 55 is here. So within this much is where your friend would win, right? Outside that is where you would win, right? Because that is a probability that that it is lying between 45 and 55, and otherwise it's outside, right? So now, okay, now let me make this even smaller. Okay, see, now you can see how much it is spread, right? That in between you have 45 to 55 is here, and rest is outside, right? Okay, now let's make it extremely high. So this is 9,000. Okay, see, now you can see that it is basically everything is between 45 and 55, right? So, and if now of course you can change it also. If you make it 49 to 51, right? If you increase the number of coins, it will come within that also, right? So in the limit where the number of coins, so let me say that this number is n. Okay, so limit n to infinity, this distribution probability becomes a delta function. Okay, what is okay? I don't know if you have seen delta function, but delta function basically corresponds to a function like that, okay, which is peaked only at one point, and everywhere else it is 0, right? Okay, and so this was with a fair coin. Okay. Now, if I say that your coin is not fair, meaning that coin is biased, so that heads comes up more. Then, if I have this same rule, okay, your friend says that its coin is more likely to be heads than tails, right? We know that, okay. And now same rule, 40 to 55. Okay, then does it matter which one you choose? Will your answer change? So I'm saying that the probability of heads is, let's say, 70%, so 0.7. Probability of tails is 0.3. Okay, same rule. So the friend is saying the same things, 45 to 55, 45 to 55. Okay. Now, which is favorable for you? Third one, right? And why is that?
Because that will be closer to 0.7.
Yeah, exactly. So let's see now. Let's make it 0.7. And now let's make the number of coins small. Okay, this is still too big. 1 is too small. Okay, let's see with this. Already with 135 trials, it's not even coming within. I mean, it's there, but it's exponentially small. Right? So it will be very small. So here it's barely visible, right? So even if there is a little bit that is coming over here, if you make the number of coins larger, so let's say now like that, then you can see it's become very tight, around 0.7, right? Whereas there's nothing over here, right? So what I was trying to demonstrate here is that for one coin, you cannot say anything, right? It can, with probability half, it can come up heads, with probability half, it can come up tails. You cannot make any definitive statement on which you can depend, right? You cannot say that, oh, I will bet all my money that it is on heads, or I will, I will be very certain that it's heads. You can't say that. But as you make the number of trials larger and larger, even though each trial is random, right? Each trial still has probability 50%. But you're increasing the number of trials, so now you can say some certain things. You can say that it will be within 50 to whatever, plus minus 1%, plus minus 5%. And you can say that with almost 100% probability, right? But if you look at this guy is basically, I don't know, the average is, average should be 0.7. And if I look at it, 5% range around that, 0.65 to 0.75, every single trial is there, right? So there's no uncertainty. Right? So you can take as many trials as you want, and the number that will come out will always be the same, right? This same thing also happens in some sense. There is another example of this, which is for even for our body, there are many mechanisms which actually depend on this, what is called law of large numbers. Okay. So, for example, whenever you breathe, okay, what happens when you breathe? There's oxygen going in. Right? Oxygen is going in. Oxygen is through your lungs, which are sort of, you can think of it as some semi-permeable membrane. Some of the oxygen is going into the blood. Right? In the blood, what is there? There are these things called hemoglobin. Right? So let me call them H. Right? There is H, and then there is oxygen. Right? I'm not going into the details of course, how the interaction works, but it doesn't matter. And now there's a probability that one hemoglobin latches onto one oxygen. Okay. Let's say that you have very few hemoglobin. Let's say you only have 4 hemoglobin. Then when you breathe, and let's say that the probability that one hemoglobin latches to one oxygen is half. Then if you just have 4 hemoglobin, then what is the probability of, number of hemoglobin which are latching, versus probability. Now the probability versus the number. Okay. So, and it's probability half again. So let's say that you have 0. What will that be? 1 by 2 to the 4, right? Just like in the coin toss. This is the same thing, right? You're tossing the coin 4 times, in the sense you have probability half whether this will catch the oxygen or not. Okay, so so this is when you have 0. This is when you have 1 by 2 to the 4 again, right? So this is 0 are latching, 4 are latching. Yeah, okay. So then I can make it, yeah. So you can divide like earlier, but okay. 4 of them are catching it. For one of them, it will be 4 times because there are 4 ways of doing that. Either the first one could, or second one could, third one could, fourth one could, right? Okay, so you get 4 again for the 3 also. There are 4 ways because the one that doesn't catch, it can be first one, second one, third one, fourth one. And then you get this. Okay, now this one is actually very alarming, right? Why? Because you are taking 20 breaths every minute. Every 16th one could be a 0, right? Every 16th one could be such that there is no oxygen that is catching onto the hemoglobin. Right? And if that happens, then you will suffocate, right? So, and this is why we obviously don't have 4 hemoglobin, right? We have 10 to the 23 or very large number of hemoglobin molecules, which means that you actually have something which is probability which is like this, right? Probability is extremely narrow. So every time you take a breath, almost always about half of them will pick up the oxygen, right? And this is why we are living. Otherwise, if this was the case, then after every 20 breaths you would die, right? So yeah, and this is, yeah. So this is one example of where the law of large numbers, the fact that as you increase the number of molecules, number of trials, number of objects, basically when you increase the number of objects, then it becomes more and more certain, right? Idea is clear, or have any questions? So the law is basically saying that, okay, the law is very mathematical in one sense, which, but look, let me make the statement and then I'll explain what it means. Okay, so I don't know if you have seen this. So they are called IIDRV. Okay, this I stands for independent. This stands for identically distributed. This stands for random variable. Okay, what does this mean? This means that I have some variables, so x1, xi, x1, x2, x3, and so on. Each of these could be, for example, outcome of a coin toss. So xi has a probability of half of being 0 or 1. x2 has probability of half of being 0 and 1, and x3 and so on, so on. Okay. So we chose we were talking about coins. That's why the probability distribution was like this. But in general, xi doesn't need to be something that is discrete. It could be probability distribution of anything. Okay. It could be probability distribution of when your bus arrives at the bus stop. Okay. That's the per time. So it arrives at 10 o'clock, probability is 50%. It arrives at 9:55, is 25%. Right? It could be some distribution. So probability of xi is this. And the important thing is that all of them have the same probability distribution. That is where this comes, identically distributed. Okay, identically distributed means that each of the xi are chosen from the same distribution. Okay, and so independent means that whatever the outcome of x1 is, it doesn't depend on x2. Okay, so for example, let's say that I toss the coin once, it lands on head, but when it lands, it gets dented. Let's say it hits some hard surface, got dented. Then the probability that when you flip it next time may not be 50-50. Because it's dented, it might change. Right? They are not independent. The outcome of the first one affected the second one. Right? So we don't want that. So we want to consider events that are independent from each other. The first one should not affect the second one. Independent identity distributed is the same probability distribution, and random variable just because they are random. Okay, that's all. And the statement is this, that if you take capital X, which is 1 by n, x1 plus x2 up to xn. So it's a sum. It's the average. The average of these guys. This average, the probability distribution of this average will look like this. It looked like a Gaussian function. I'll tell you what a Gaussian function is. I mean, you might already know probably. So probability distribution is equal to 1 by normalization factor. There's some normalization factor. Usually it's written as n, but I'm using n over here, so I don't want that. So I'll just make it proportional to, okay? Proportional to exponential minus x minus mu whole square by 2 sigma square. This one have you seen? Gaussian? No, not so much. Huh? Okay, never mind. So so the probability distribution looks like this for this guy. Okay, so where should the mean be? So let's say that this had a mean at mu. So this, what should this be? Mu also, right? Because see, this is just a sum of these guys, right? So if the mean of each of them is mu, right, then the mean of the full thing will also be mu, right? So this is at mu, okay? And this guy, this one, the width, which is what we have been looking at, like for example, this width, right? This width is given by alpha divided by square root n. This is called central limit theorem. There's a proof also of it. The proof is a bit complicated, so I don't want to go into it. Just explain the statement. Right? So what this is saying, see, n is the number of trials. For example, it's the number of coin tosses that we're talking about. Right? So if capital N increases, what happens to this guy? This is 1 by square root n, right? So it reduces, right? So this becomes thinner and thinner and thinner. If n tends to infinity, what will happen to this? This will become infinitely thin. Which means that the probability of capital X being equal to mu will become 1. Basically, it become increasingly certain, right? So the underlying thing is random, right? X1 is random, X2 is random, but this variable, which is actually made out of random numbers, is certain. And it's increasingly certain. So it's very strange, right? It's very counterintuitive. The more random numbers you add, the more certain the outcome becomes. Right? Right. And that is what so this is known as central limit. Okay. So maybe I should take this up. Huh? Yeah. Wait, actually, let me do one thing. Let me show one more simulation and then I'll take it up. Huh? Okay, so all of you have studied about pressure, right? In physics. So what can you say what do you understand from pressure? Like how do you think of pressure of a gas? Force, right? Force exerted on the wall, right? Okay. And how do I think about it? So we know that the gas is made out of some molecules, right? So how would you, in terms of those molecules, how would you think about pressure? Rate of change of momentum, right? So you can think of it as how much momentum is being exchanged. So this is the wall that you were referring to, right? And these are some molecules, and I've made them as spheres for now, right? And they are hitting the wall. And that is what is registering the pressure, right? Because that is the force applied, right? Rate of change of momentum, right? So if this one is losing momentum in the sense that the momentum is getting reversed, so there's a momentum difference, right? It's coming in with plus p, is going out with minus p. I mean x component, y component is still the same. So that much momentum is being imparted to the wall, correct? And that is the force, and that is now that's the measurement of the pressure. But this doesn't look exactly like pressure. Why? Because if I take a balloon, right, you fill it with gas, and it has some pressure. The pressure is more or less the same, right? It's not that suddenly the pressure is reducing or it's increasing, because the shape of the balloon is more or less the same. If the pressure suddenly reduced, then the balloon would become smaller. If suddenly increased, it would suddenly become bigger, right? But now let's say that inside the balloon there are only 5 molecules, like this, 5 molecules. This is the surface of the balloon. So the wall of the balloon is getting so much pressure. So now during this time, there was no change in momentum, and now suddenly there was a lot of change, right? and again nothing is happening for some time. And then again something will happen, right? But this is not the experience that we have of pressure in our world. We don't see pressure fluctuating. For us, pressure more or less stays the same. Right? So let's see why that's happening. Now, very simply, why that's happening is because inside the balloon there are not 5 molecules, right? There are 5 to 23 molecules. So 5 into 10 to the 23 molecules, right? So let's try that. So let me make it, so this is a very large set of molecules, but there's still a problem. Okay, you see that these molecules all started in a particular place, they all had a particular velocity, so they're moving around, they're bouncing against the wall. Again, there was one time for which there was very large pressure. Again, there is very large pressure, right? But okay, now that window is sliding, that's why these things are juggling. But okay, but the point is that there are intervals where there is no momentum exchange. Again, that's happening. So what would happen to the balloon in this case? So if you start with the balloon, there are these particles at one end. Okay, they are going, they're hitting, and then they're coming back. The shape of the balloon itself would change. Correct? See, when these particles are hitting, there's a lot of force, so the wall will expand. Right? When they are not hitting, there is the environment which is putting pressure, so it will compress. And then it will go. So it will do this sort of motion. That's also not what we see. We don't see that the balloon is oscillating. Right? It's not breathing. Right? Right. But we have we still have a large number of molecules. So what is going wrong? Yeah. This is all constant. Yes, exactly. Right. But then the question is that let's say so when you're filling the balloon, right, you can think that there is a nozzle and they're all going in one direction, right? So then if we sort of approximate it like that, then you can think that they are all, right? But with time, what happens is that what you're saying happens, right? That given enough time, they all start going in random directions, right? So how does that happen? That happens because they are, so there's one very important thing over here which is very unrealistic, okay? Not sure if you have noticed that the particles are actually passing through each other, right? If you look at it, so now look at when it bounces. You see these things are passing through each other, right? That is not realistic. Okay? If there are two, there are going to be collisions. When the two molecules are coming close together, they are going to collide, right? So now let's see what happens if I turn on collision. So now collision was off and then now I turned on collision. Okay, so immediately they started hitting each other. Right? They start hitting each other and going all over the place. Right? Now just wait for some time and then you'll see that this actually becomes more or less flat. You won't have this business of suddenly a lot of them and then none of them, lot of them, none of them. Right? Now you can see it has become roughly flat. Right? And it is more or less fluctuating about a mean. It's still fluctuating quite a bit. So if you consider that this red line is the mean value, then the highest one is around maybe 50% greater and the smallest one is 50% lesser. That is also quite extreme. Like if you have the balloon and suddenly there is 1.5x pressure and sometimes there is 0.5x pressure, right? Then also there will be some movement, right? Because the pressure inside is not constant. Right? But again, that is not what we see. So now and that is because this number of particles, 687, is too small. So let's see what happens if I just max it to this, right? Okay, so now it's equilibrating. So it's reaching equilibrium, right? Equilibrium is reached when you can say that every particle is everywhere with equal probability, right? And there will also be a distribution of the velocities. Okay, so now you'll see, now it's still equilibrating, the mean will come down and it will stagnate. It will be invariant in time. Yeah. Okay, so now you can see that the difference is not that much. Earlier we were saying that the deviation from the mean was 50% up and 50% down. Right? Now it's more like 30%, 20% or something like that. Right? So it's becoming smaller. And again, it's the same effect. It's the same effect over here. And how is it the same effect? Because once it's thoroughly mixed, by mixed means that there has been sufficient collisions and things become sufficiently random, then you can say that position and velocity of each molecule is a random variable. They're all identical, so it satisfies this, and they're all independent, right? Because at any given time, it can be at any random position, right? And so the same thing applies over here, that this 1 by square root n that you get over here, that applies now in pressure. So pressure will become more and more certain based on what the what the number of particles is, right? Obviously, this is not realistic still, because this is only 1000 molecules, and we want, in real life, we want to think of 10 to the 23, which obviously I can't do a simulation of because the computer cannot do that. But in that case, when you have that many molecules, what will happen? You will have this mean, which is a red line. You will have tiny fluctuations around it, but they'll be so small that you can't even see it. Like, just think about it, right? This is square root n. If n is 10 to the 23, what will be square root n? 10 to the 11.5. Yeah, 10 to 11.5. 10 to 11.5 is like 0.000, like 10 zeros, right? So so that is the level of certainty that you have. And that is why in our world, when you are looking at this balloon, you don't see any fluctuation. If you measure the pressure, it's constant. Right? Our pressure gauge, like we are using some pump or some probe to measure the pressure, it will give you some, I don't know what is one atmosphere plus minus 0.001 or something like that. That might be the error but actually the certainty is much higher than what your pressure gauge is saying, because of this phenomena, that it's all very very certain, right? Okay, I can also change. Right now what I'm doing is, this is bin size is 0.2. This is actually calculating the pressure by taking the difference in the momentum in every 0.2 seconds. If I make it larger, it becomes even more, okay, see, now you can see that it is fluctuating even less, right? It has become even tighter. Why? Because there are more collisions per unit time. I'm saying that the unit time is now 0.5 seconds, and what is being plotted over here is the number of things that are hitting or changing, the change in momentum in 0.5 second. Right? So that is what has come over here. Right. Okay. So any questions about this? You got the gist. Gist is just that you have the more particles you have, the more independent random variables that you have, the more certain it becomes. Right. Now, what was the difference when I switched off collision? So let me say I just switch off collision. Actually, now it won't change. I have to restart this thing, reset, and now collision is off, right? So here, the thing with when you don't have collisions is that it's not random. Okay? This thing goes away, random variable. For example, if I ask you, if I give you a pendulum, right, and I say that tell me where it is at a particular time. Let me just pause this. Okay, it will go. So, and I ask you that the pendulum, where it is at a particular time, you can tell me the answer definitely. You don't need to say that it will be here with some probability, right? Because the pendulum has a periodic motion. It starts at one place, it goes to another place in some time, it comes back to this place, it goes to that place and back. These things are doing the same thing, if you notice, right? It starts here, it goes there, it bounces, comes back. So they are doing a periodic motion. When you have periodic motion, this part breaks down. It's not a random variable anymore. And that's why you can't talk about probabilities, right? So the fact that you have collisions, that is what makes it random, because if you have millions and millions of collisions, right, finally the one particle has been hit so many times that has effectively become a random variable, right? So yeah, and that's what we saw. This statement is quite hard to prove, but this is what we see in most experiments. There are certain cases for which it's well known, right? Like over here also we saw that if you wait for enough time, then it basically approaches a mean, and then around the mean there is some fluctuation which is a random variable, right? Yeah. Okay. So then why don't I stop this? Now there are ways to actually, now where do I keep the chalk? Here. Okay. So there are ways to use this idea. So let's say that you want to calculate some integral. You want to calculate, let's say, area of a circle, right? So how would you calculate area of a circle? So you take some patch, you take this guy, you take some ring, you say that this is dr. Okay. What is the area of the strip? It will be, this is at some distance r. It will be 2 pi r dr. Correct, that's the area of the strip. You will integrate the area of the strip from 0 to capital R. Okay, to get the, yeah, exactly. So this will give you pi r square, right? Right. So what I'm saying is that, let's say that you didn't know pi r square and you want to calculate pi r square, right? So then you will break the circle into rings, right? Each ring has a circumference of 2 pi r and width of dr. So the area of the strip is 2 pi r times dr. You add up the area of all the strips and you will get the, you can see that this works out, right? Because integral of r will be r square by 2. 2 will cancel and you will get this, right? Okay, so this is how you can calculate pi. There are, and now see, pi itself is a magical number, right? Someone told you that pi is this number, 3.1415, whatever it is, right? But let's say that we didn't know what pi is. Then what can you do? You know that area of circle is equal to this. Okay. So let's say that I make a square. I make capital R equal to 1. So I take this thing to be 2. Then R is 1, correct? From here to here. Capital R is 1. Now if I plug in capital R equal to 1, then I will get pi. Okay. But now the question is that how do you calculate the area? So now there are many ways. What you can do is one very simple trick, which you can tell me if it's going to work or not, is that you take this, make this a square plate, some square plate, and you put a lot of grains of rice. You spread it uniformly. Okay. Then for each grain of rice, you just measure what the distance is from the center. You know that, okay, so let's say that you know that you put 10,000 grains of rice, right? You measure how far each guy is, right? If it is within a distance of 1, then you count it, otherwise you don't count it. Okay. So then this is number of grains which are less than 1 away from the center. Right. This will tell you what pi is. This will tell you to some certainty. Right. Because there are 10,000, so this obviously cannot represent a real number. This will be some fraction. Because this is some integer, whole number, and this is a whole number. So it will give you some fraction. It's an approximation to pi. And now let's see what would happen. What would happen if you do this for increasing and increasing number of grains? Okay. You can find that. You can also find this simulation on YouTube later. But let's say that I take this and I randomly just drop one grain of rice or one marble or something. Okay. So on this plate, or let's say I just have some, I mark out 1 by 1 meter or 2 by 2 meter of my carpet, and I'm dropping some marble or something like that. If the marble is within 1, right, then I say plus 1, otherwise I say that it's not there. Okay, so I'm saying number of, the same thing basically, number of grains in less than 1 divided by number of total grains. Correct. So let's say I'm just dropping 1. What are the outcomes? What can this be? Denominator is 1. Numerator will be either 0 or 1. Okay, because it's either less than 1 or it's not. So there are two options. It will be either 0 or 1. Now let's say I drop 2. Denominator will be 2. Now there are 3 options. Either it can be 0 by 2, it can be 2 by 2, or it can be 1 by 2. Again, you can see that the same thing that happens with the coin is happening, right? Things are appearing with probability half, right? Or no, so this is not probability half actually. The probability will be given by this exactly, by pi. Right? So this is a random variable whose average is pi. Yeah.
So in the dice example, 10,000 is the total number of dice games.
Yeah.
So then the number of dice games less than 1. Won't that always be less than 10,000?
Yeah, that will be less than 10,000, right? So this thing actually will give you pi by 4, because this is actually giving you area of circle divided by area of square, right? Because what you are doing is this entire thing, all the grains are falling within the square, right? Out of that, some subset are falling within the circle, right? So this will give you area of circle divided by area of square, and this guy is equal to pi by 4, right? Because this is pi times 1 and 2 times 2, right? So this will give you whatever pi by 4 is, and then you can multiply by 4 to get value of pi, right? Correct. And so this is the same thing in the heads tails example also. We had a percentage, right? Or we are saying what fraction of the coins are landing as heads. So that fraction was also between 0 and 1. Okay? They are between 0 and 1. So you do this, and then again, and you keep doing this. Right? So keep putting 1 by 1, 1 by 1, 1 by 1. And what you will see is that if you look at number of total grains, number total, this is pi by 4. Okay. And I take this guy and I put it on this axis. I'm plotting that guy on this axis. First, I will see that if I'm just putting 1 grain, I do this. So I am doing this many times. Let's say that I just drop 1 grain. I see where it is. Then I start again. I pick it up. I drop it again. I pick it up. I drop it again. Then you will, on average, your number will still be pi by 4. Okay, but the error bar will be very large. By error bar, what I mean is that the variance, right? The probability that this thing is coming out to be pi by so this thing will always be either 0 or 1. Right? It will be some distribution with probability pi by 4. It will be 1, and with probability 1 minus pi by 4, it will be 0. Right? If I'm just dropping one marble, correct? This has a very wide distribution. For example, so if you calculate the standard deviation, so the sigma is equal to square root of average of x square minus average of x whole square. Right? This you might have seen in statistics or probability, right? And and then this will be very, very, very wide. Right? This will be some large number. It will be this large. If as you increase the number of total, this will become smaller and smaller. And again the same thing. It will become smaller as 1 by square root n. And this is what we do. This is what we do for problems which we cannot solve by hand. For example, here we could calculate what pi r square is, right, by doing this integral. Let's say that you have some problem which is very difficult. So dx, dy, dz, I don't know, x square sine y tan z and okay, I don't want to make it separable, x square plus y square, some very complicated function. Some integral that maybe you could do with a lot of trigonometry tricks, but let's say that it's very hard to do, right? Then what you can do again is you can use this trick. You say that this is my probability distribution, and I'm going to throw objects with some probability, and then I'm going to calculate this guy, right? So yeah, and that comes back to the same thing as what we did over here for the calculating pi. So, and this is used very often for things that are very, what do you say, this is just 3-dimensional, but sometimes you can have things that are many dimensional. For example, for the gas, right? For the gas, we had large number of particles, like 10 to the 23 particles. Okay, so you have 10 to the 23 particles, and you want to calculate the average position. Let's say you want to calculate the average position. Then you have, so each particle has x1, so xi, yi, zi is the position of each particle, right? And so you will, and the probability of a particular configuration. So particular configuration, also actually the Vxi, Vyi, Vzi. It also has 3 velocities, right? It has the position in xyz and velocity in xyz. Okay. Now, what do we want to calculate? We want to calculate, let's say, average position. Okay, so what we want is capital X is equal to sum over I xi, capital Y is sum over I yi, capital Z is equal to sum over I zi. And the probability is something complicated. Let's say the probability of this is something complicated. It's some function of all of these things. Then the way you will do it is that you want to calculate something like this, integral of, let's say I just want the average position. Then you want to calculate this, okay? And this is a function of all of them. So basically x1, y1, z1, these are just for the first particle, okay? vx1, vy1, vz1. And then you will also have x2, y2, z2, and so on. So it will be the entire thing. Now this is very hard to calculate, okay? But what you can do is that you can just pick one particular value of all of these things. So you can pick one configuration with this probability, right? You pick it with this probability, and then you calculate what the capital X is for that, and then you store it. And you do this many, many times, and then you add it up. If you do that, you will end up with an estimate for this. You will get some value which is approximately the same as this. And it will become more and more certain as you increase the number of trials, again going as 1 by square root n. Right. So, okay, now this is a bit, I might have to give one particular example to explain this bit further, which I'll do. But this was very instrumental because actually this has a very interesting history also. After people figured out how the sort of atomic bomb works, right? They didn't know what would happen. So they knew that if you have some kind of fission, then there's a particle that is breaking up and releasing some more particles that are going here and there. But after that, they don't know what happens, because that might hit another 2 particles, that might hit another 2 particles, that might hit another 2 particles, right? And things will keep going further and further. But there are too many paths. For example, there's one here, there's one particle here, here. Okay, then this might decay and send out something, that might hit here, this might decay and send out something, then this may not hit this, but this one may hit this, and that might send out something, that might send out something, right? So these are all just some, yeah, whatever uranium atom that is sending out a, what do you have? Yeah, so it's this fission that is sending out some particles, right? And that is propagating. Now, if you want to calculate what happens, you can't really do it, because if you want to sit down and calculate by hand, then you have to calculate every single path, that what is happening in each path. And number of paths is astronomical. You just can't do it, right? So this is what prompted the invention of this method. So at that time they said that, why are we calculating every path? Let's just take a random set of paths. The total number of paths might be 10 to the 23, doesn't matter. Okay. Let's just look at 1,000 random paths and let's just see what the average of those is. And it's good enough. You do that 1,000, you take those 1,000 averages, and that's already enough. For example, for pi, so pi we know has infinite digits, right? And but the thing is that most of the time, we don't want to know all the infinite digits. We just want to know maybe the first 3 or 4. Because you want to compare to some experiment in a physics lab. The experiment has only that much resolution. It only has the first 4 or 5 digits. So it's not useful to know everything, know all of the digits, right? So then what you can do is, you just take this square, right? You drop 10 to the 8 marbles on it. This can be done very easily on a computer, right? And already you know pi to first 4 digits. Why? Because this will give you a certainty, which is given by 1 by square root n, 10 to the 8. So you 10 to the 4. 1 by 10 to the 4 is 0.0001. So you know 4 digits. Okay. If you do this procedure, you will find that pi is something like this: 3.141 plus or minus 0.0001. So maybe one more digit is there, 146. Okay. You will know it to this much accuracy. Right. Right. Okay. So, yeah. So, should I, is it time? Wrap up? Okay. Yeah. So, basically, that's what I wanted to explain to you guys, that we are used to thinking that everything should be known exactly, right? So, for example, if I give you a problem of a pendulum, you can solve the equation of motion. Right? You can draw the graph of what x looks like, what v looks like, right, as a function of time. If I give you a double pendulum, you guys have heard about double pendulum? So, double pendulum is like this. Okay. And you impart this with some velocity. There is gravity in this direction, and then you can try to plot the position x and y coordinates as function of time. It can't be solved exactly, and this is what is known as a classic chaotic system, because you cannot find an expression for what it will do at very long times, similar to like what we have for simple pendulum. Simple pendulum is just this. Right. And most things in the world are like this, where if you try to sit down and you try to look at the very, what do you say, you go down to the smallest level and you try to write the equation of motion. Technically, the equation of motion is correct, but you can't use it for anything. You cannot use it to make any predictions, right? And that is where actually saying that maybe I don't know what exactly is going on, but let me just say that it is represented statistically by a probability distribution. Right? That is enough. And that works. That works beautifully in most cases, because most everything in our world follows the central limit theorem, which is that it is a collection of identical objects. So I talked about molecules in a gas. Actually, the same idea also applies to flocks of birds. So if you have some collection of birds that is flying in a particular direction, right? So they will also have a little bit of randomness, because one of them might see the next one and try to move in a random direction and things like that. If there are enough of them, you can apply the same logic over there. Right? The same logic even applies to stars in a galaxy, provided there are enough of them. So if there are, let's say, 10 to 6 stars in a galaxy, then again their motion can be considered to be some random collection of random variables, right? So this idea is very powerful, and it is there almost everywhere. One of the things that people use it for a lot is to, in fact, even decide how to make roads, because the number of cars that you will have on the road at any given time is also a random variable. For example, everyone goes to office at 9 in the morning, but everyone is not leaving exactly at 9. So I am getting out of my house, but I might think that, oh, my shoe is broken or something like that. So I need to get another pair of shoes. So I lose 3 minutes, right? So I started 3 minutes late. Somebody else might be starting exactly on time. Somebody else might be starting early, right? So even though everyone is roughly starting at the same time, there are random events in people's lives because of which things are slightly off. And because of this, statistically, you will always find the same number of cars on the road, right? If there's traffic at a particular place, that same traffic is there every day. It's not going to happen that one day it is suddenly empty because everyone started early, or one day it is very crowded because everyone started late. So this, you see this kind of random behavior in our world every day. So that is what I wanted to highlight. And yeah, you can ask me any questions if you have any. Yeah, was it understandable? Were you able to get the big picture of this? Okay. So yeah, so I'm done basically. Any questions? Yeah. So the double pendulum is, it doesn't have periodic orbits, in a sense that if you give it enough time, right, it's going to go everywhere. For pendulum has got periodic orbit, in the sense that it starts somewhere and it goes back to some path and it comes back. Okay. So for example, if I so this is the momentum and position. So this is theta, and this is theta dot. So p theta, momentum or derivative of theta. Okay. So this is speed, right? And you know that the energy is conserved because it's v square plus, right, kinetic plus potential. So in the pendulum, it goes like this and it comes back. So there's some place where the momentum is high, theta is 0. That's this point. Speed is highest, right? Then there's this point at which theta is highest, but speed is 0, right? And then so it goes back and forth, and it keeps on traveling around this. But there are many other positions that it could take. For example, it could take this position, this position, all these different positions it could take. But it doesn't do that. It just keeps on going in one periodic orbit. Right? For the double pendulum, this will not be two-dimensional, it will be four-dimensional, because you will have theta 1, theta 2, p theta 1, p theta 2. Okay, it will be four-dimensional, and there, if you allow it to go for some time, right? If given enough time, it will go everywhere. In every single value of theta 1, theta 2, theta 1, p theta 1, p theta 2, it will go to every single value. And that is what is called a chaotic system. Because yeah, given enough time, it visits every possible configuration. And that is not true of things like the simple pendulum. So there are two classes of systems. They are called integrable, which that word comes from some old way of thinking about this, and chaotic systems, which is mostly like, and in the example of the gas also, when there are no collisions, that is integrable, because there also the particle doesn't, each particle doesn't go everywhere. It just goes in one rectangle like this, like this. Whereas if I put on collisions, then they all scatter amongst each other, and then given enough time, every particle will go everywhere. It will go everywhere and it will have every possible velocity that is within the range of energy.
Historical question. So
yeah.
Monte Carlo stuff.
Yeah.
Edward Teller.
Edward Teller. So it was Stanislav Ulam who basically came up with this idea. It's also very interesting how we came up with it, because he had some very he had some disease or he had been poisoned or something, and then he was in hospital, and his friends told him that you should take rest and not work. So he was playing solitaire. So you know the game solitaire, right? Where you have these lot of cards and you have to arrange them in sequence. So he started thinking that why. So this is a very general question. Like, if you look at a solitaire on your computer, why should it be solvable? So solitaire means that you have certain sets of card arrangement and you have to arrange them in sequence under a certain set of rules, right? That only a higher number can come only on top of its next subsequent number, right? That sort of thing. So why should it even be solvable? If I set the cards in a random position, it may not even be possible to bring them back into the sequence given the allowed moves, right? And then he started thinking of this question of what is the number of ways in which you can arrange cards so that they are solvable solitaires, right? And it's not easy to think about this. So then he thought that, okay, why don't I just lay out a solitaire 100 times manually? So he just manually sat down and laid out the cards 100 times and he tried to solve each of them. And then he figured out that, okay, 5 out of 100 can be solved. And that's how he thought about this method, the Monte Carlo method. So yeah, and another interesting thing, it's called Monte Carlo because Monte Carlo is a very famous place in France on the French coast, which is famous for the biggest casino in the world. Right? And basically, casinos or gambling is a matter of chance. Right? It's just luck. So it depends on if you're lucky, you can make a lot of money or you can lose it all. Right? So that's why they call it the Monte Carlo method, because this was the first time that somebody in physics said that we don't need to exactly solve things. We can actually just think of it as a random number, and then the answer will come out by itself. Right? So this was the first time that randomness was introduced in physics. And yeah, and the very interesting thing is that actually the motivation, the first physical example for which it was used was to understand the atomic bomb, and that was very interesting how there are some no problem. Yeah, there's some very interesting events, how events drive science. Right. Okay. All right. Okay. Thanks.